Swayam Prabha. Digital India. Educated India.
We also said it's unique. Actually, uniqueness is pretty easy to see, and that's because of from a simple counting argument. So remember, we said R and S, we're going to restrict to just the range 0 to A and 0 to B respectively. So there are A of possible values of R and B possible values of S. So altogether, there are AB possible values of the pair R comma S, right? And we already just now argued that for no matter which one you pick, there is a solution. RS has a solution, this equation has a solution for RS. So every RS has some X that satisfies the equation using RS. On the other hand, how many, so I want to prove that modulo AB, it has only one solution, right? At most one solution. So how many possible X's are there? Well, there are only AB values of X modulo AB, right? So 0 all the way to AB minus 1. And each X is, given an X, I can take its remainder modulo A and remainder modulo B. And that is a unique remainder, in these ranges for X, right? So X can correspond to at most one RS. In fact, it will correspond to one RS, and whatever is the remainder of X with respect to A and with respect to B. So every X is solution for at most one pair RS, and every RS needs at least one solution. There are only there are equal number of pairs RS and values X. So you cannot have a pair RS claiming two solutions, because if it took two solutions, there will be some other pair RS which will be left without a solution, because each X can provide for only one RS, and if some RS is greedy and takes two solutions, then there will be some other RS left without a solution. Since we already argued existence, that cannot happen. Okay, so that's a reason that it's unique. All right, so yeah, so the reason it's unique is basically a counting argument. The number of possible pairs RS is the same as the number of possible X's in this range. So this, one-to-one correspondence between this, saying that any number X has a unique RS representation, and once you give me an RS, it corresponds to a unique X. It totally tells you what that X is, right? It tells me that here is a way to write down or represent elements in ZAB, right? Modulo AB. So give me any number X in ZAB. I can instead look at its remainder with respect to A and its remainder with respect to B. So I get two numbers. So that's a pair in the set ZA cross ZB. And that's a unique representation. So clearly every X has such a representation. And conversely, every representation corresponds to a single X. No two X's will end up claiming the same RS, right? So it's an alternate representation. Instead of writing down the integer X, now you can write down the pair of integers AB, and that has all the information about X. Okay, so this is what Chinese remainder theorem tells us, that every X in the range ZAB, where A and B are co-prime with each other, can be written as a pair of integers, one modulo A and the other modulo B. And it's not just that, so clearly given X, you can easily figure out its representation R and S, but it's also efficiently invertible representation. Somebody gives you R and S, you can, solve for x efficiently. And what it involves is the extended Euclidean algorithm required to find this u and b. All right, so what is this useful for? So we'll see several uses, but let's see a couple of them right now. So let's assume we are given such a, we are interested in a modulus AB where A and B are co-prime with each other. Okay, so I'll just put it up there. And yeah, how do I simplify the arithmetic modulo M? The idea is that I can now use arithmetic modulo A and modulo B separately. These are smaller numbers, and use them to carry out the computation modulo M. Okay. So again, given how the first step in doing that is whatever numbers I'm given that I need to do arithmetic on, I would use their CRT representation. And then I'm claiming that addition and then I'm going to stay in CRT representation, right? I'll do the computation and I'll get back CRT representation of the result. So in particular, if you want to add two numbers, I will go to their CRT representation and do coordinate-wise addition to get the CRT representation of the sum. And similarly for multiplication, I will do coordinate-wise multiplication. So you give me x and x prime, and you want to find x plus x prime. What I'll do is I'll just find the CRT representation of x plus x prime. And how will I do that? I will just, so if you, first I'll compute the CRT representation of x with respect to A and with respect to B. I'm just showing you modulo A here. So the first coordinate in the pair that represents x in the CRT representation is the remainder of x with respect to A. And the second coordinate is remainder of x with respect to B. So here's the first coordinate for x. Here is the first coordinate for x prime. If I claim that if I simply add them up, modulo A, what I'll be getting is the CRT representation of x plus x prime, the first coordinate of that, because the remainder of x plus x prime modulo A is simply r plus r prime modulo A. Right? So this is just modular arithmetic we already talked about. X plus x prime is congruent, if x is congruent to r and x prime is congruent to r prime modulo A, then x plus x prime is congruent to r plus r prime modulo A. And similarly for B. Okay, so that is the addition. And yeah, so I could write it this way. So to do the, so here the plus with M written here, it does stand for addition in ZM, but in the CRT representation. Right? And so if RS is the CRT representation of X and R prime is the CRT representation of X prime, then this is the CRT representation of X plus X prime, where again, these are additions modulo A and B. So in ZA and ZB. Okay? And similarly for multiplication, again, it's the same kind of argument, a remainder of X times X prime modulo. So X times X prime is congruent to R times R prime modulo A if X was congruent to R and X prime was congruent to R prime modulo A. Okay, and again, there's something you can quickly verify by looking at the remainders. Okay, so the net result is that instead of doing multiplication modulo this larger number, I can do multiplication modulo these two smaller numbers. And maybe that's all I need. I need not go back to the original representation. If I'm going to do a bunch of computations, I can keep it in the CRT representation until I'm done with all the calculations, and then I can go back to the representation modulo M. And it's not just addition and multiplication. I can do additive and multiplicative inverses also using this coordinate-wise representation. So firstly, the additive identity 0 has a CRT representation 0, 0, and the multiplicative identity 1 has the CRT representation 1, comma 1. So they are pairwise, they're coordinate-wise identities. And then the inverses are also coordinate-wise. Okay, for instance, consider additive inverse of RS. Suppose the additive inverse of RS is R prime, comma S prime in the CRT representation, which means R plus R prime should be equal to 0 modulo A, and S plus S prime modulo B should be equal to 0. In other words, R prime and S prime are the additive inverses of R and S in their respective sets, right, in ZA and ZB. Right, so these are, R prime is the additive inverse of R in ZA, and S prime is the additive inverse of S in ZB. And similarly, you find multiplicative inverses. Well, if multiplicative inverse, multiplicative inverses don't always exist, modulo some integer m, but when they do exist, so suppose RS is a CRT representation of a number which has a multiplicative inverse. Then let's find out what that multiplicative inverse is. It has some CRT representation, say R prime S prime. And what we know is that since multiplication is coordinate-wise, again, R times R prime should be equal to 1, right? Which means R prime should be the multiplicative inverse of R in ZA, and S prime should be the multiplicative inverse of S in ZB. So if you look here, as I said, not every integer has a multiplicative inverse, right? Which ones do? Here is one way to think about it. So you need to have multiplicative inverses for the for R and S, for both R and S. That's when you'll have multiplicative inverse for the full pair R comma S, which means, and these are prime numbers in our particular example, Z3 and Z5, 3 and 5. And we already saw that every integer in the range 0 to say 3 minus 1 or 0 to 4 minus 1 except 0 has a multiplicative inverse when we are working modulo prime, so 3 or 5. So which means 1 and 2 both have multiplicative inverses. Modulo 3 happen to be themselves, and 0 doesn't, right? So, and similarly for Z5, 1, 2, 3, 4 all have multiplicative inverses, 0 doesn't. So if both R and S are non-zero, then it has a multiplicative inverse, and if one of them, even one of them is 0, or if both of them are 0, in either case, it doesn't have a multiplicative inverse. So 3 doesn't have a multiplicative inverse modulo 15, 5 doesn't, 6 doesn't, 9, 10, 12, 0, none of them do. The others all do, right? So that's, these are the elements in the range 0 to 14 which have multiplicative inverses. And we'll have more to say about these numbers. Yeah, but in terms of which ones they are in using CRT, there is a very simple characterization. At least when R and S are prime, sorry, at least when A and B are prime numbers, distinct prime numbers, then it just means in the CRT representation, neither coordinate is 0. That's when it has a multiplicative inverse. Okay. Yeah, so multiplication, so an element X has a multiplicative inverse modulo M if and only if it has multiplicative inverses modulo A and modulo B. In fact, this is something you could have, we already talked about when a number has a multiplicative inverse modulo M. That's when it is co-prime with M. And then, from there directly you could have deduced this without knowing the Chinese remainder theorem. So that's just the statement that X is co-prime with M if and only if it's co-prime with A and it's co-prime with B, provided M equals to A times B. And here you don't even need A and B to be co-prime with each other. This statement holds as long as n equals to a times b. So that's something you could just verify by yourself without resorting to CRT. But CRT tells you also when the inverse exists, how to find the inverse, provided you can find the inverse modulo A and modulo B. We'll conclude with one more thing. So we'll extend the Chinese remainder theorem beyond product of two factors. So here I've written m as a multiple of n factors, a1 to an, such that every pair here, ai, aj, are co-prime with each other. Okay? And the claim is, so for the CRT was originally for n equal to 2, but the same claim holds for larger n. So the claim is that you give me any r1 to rn, each ri in the range 0 to ai, then there is a unique solution for this system here that x is congruent to ri modulo ai for all I equal to 1 to n, and this solution is unique among numbers in the range 0 to n minus 1. Okay, so n equal to 2 is exactly the statement of CRT. And I'm going to now show you a proof for arbitrary n. And I'll first prove existence. Uniqueness will be easy consequence. So, and for the proof, I'm going to use weak induction. And we will use the original CRT for n equal to 2. We'll use that in our induction step. Okay. Our base case is going to be actually a very simple case, n equal to 1. So this just says m is equal to a1, and you're given a single equation saying x is congruent to r1 modulo a1. So you can pick x to be r1 itself, and it is a solution in the range 0 to a1 minus 1, so 0 to m minus 1. So that's the base case. So here is the induction step. So we'll prove that for all k greater than or equal to 1, if it is the case that systems of k congruences, right? So I equal to 1 to k, if they have solutions where the AIs are co-primes and RIs are arbitrary, if every such system has a solution for up to k congruences, then even for k plus 1 congruences, there will be a solution. Okay, so here the case where I'm making the induction hypothesis for when k equal to 1, my hypothesis here is that every system of 1 congruence has a solution, and that was indeed my base case. So now suppose for some arbitrary k greater than or equal to 1, this is the case that up to k congruences, the systems have solutions. And then I need to prove that, you give me an arbitrary system of k plus 1 congruences, it has a solution. So suppose this arbitrary system you're giving me, there are k plus 1 factors which are co-prime with each other, and arbitrary numbers r1 to rk plus 1 used to define the system of congruences. I need to find you a solution. I need to prove that there exists a solution. So I'll tell you how to find the solution. For that, first I will define a smaller system with k congruences. And the moduli are the first k of these k plus 1 moduli. And the r1 to rk are exactly the same, r1 to rk, the first k of the numbers you give me. Okay. And now this is something to which I can apply the induction hypothesis. And it tells me there is a solution for this system. So I pick that solution. Solution is in the range 0 to product of these minus 1, but doesn't matter. Just need to know there is some solution, some integer that satisfies this system. And I'm going to now define another new system. And it has only 2 congruences. And the two congruences are the following, and two moduli. The two moduli are, I'm calling them A and B. So A is A1 to AK, and B is just AK plus 1. Okay, so the first thing to note is that A and B are co-prime with each other. And the reason for that is AK plus 1 did not have any common factor other than 1 with any of these A1 to AK. So it doesn't have any common factor with their products either, with their product either. Right, so A and B do not share any prime factors or any factors greater than 1. And the two systems I've defined, the two congruences I've defined in my system is, X is congruent to S modulo A and congruent to RK plus 1 modulo AK plus 1. So this was a thing I had kept aside while defining the smaller system. So that now shows up as the second congruence in the new system I'm defining now, right, the smaller system. And here, now I'm going to use CRT to get a solution. So this is a setting where I can apply the CRT. A and B are co-prime with each other. And, so there is an X, there exists a solution X that satisfies both these, okay? So take that solution. I'm claiming that this solution, this X that I just now obtained, which satisfies these two congruences, is actually a solution for the original system involving K plus 1 congruences, okay? And I will leave it to you as an exercise to prove that. But it's not very hard. And the basic observation is that, look, you got a solution here that satisfies these two congruences. In particular, it satisfied this one, which is good. This is one of the K plus 1 congruences we want to satisfy. And this other congruence that it satisfied tells us it's congruent to S. And we know something about S, that S satisfies the other K congruences we want to satisfy. But those congruences are with respect to various A1, A2, and so forth. Whereas this one is with respect to their product. Okay, so you know that X satisfies this congruence with respect to the product, and A1 is a factor of A1 divides A. From these two, you should be able to conclude that X and S actually are congruent to each other with respect to the modulus A1 also. And since S is congruent to R1 with respect to modulus A1, that would mean X and R1 are congruent to each other with respect to modulus A1, right? And similarly for R1 to RK. So that's, I want you to think that through and, prove this part and conclude the argument.